Okay, now let's consider the same picture as before. That is, we have this picture, but let's consider what happens if we move in the x direction. So let's ignore the y and move delta x in the x direction. Now the coordinates of this point are the same as before, x naught, y naught, 0. We move in the positive x direction. The way the picture is drawn, this motion is in the positive x direction. It could be positive or negative, but the positive x direction is out here. Moving through displacement delta x, we move from x naught, y naught, 0 to x naught plus delta x, y naught, 0. The value of the function at that point will be f of x naught plus delta x, y naught. In other words, we're evaluating the function at the x and y coordinates here. Similarly, back here, the value of the function is f of x naught, y naught, the same as it was before. We can draw a projection parallel from this point back to this line at right angles, and we can construct this triangle. Now, did this before in the video, didn't operate, so we're kind of going back over it. I don't want to take the time to redo it at this point. I also made a mistake when I got here, so let's just have that front and center. Let's consider the orientation of this triangle. Now, positive x direction is here. We're used to the positive x direction going from left to right, so that when we view this thing from the side, we're going to see the x direction going this way, and the graph is going to go downhill. It's going to be higher at the initial point than it is at the final point. Now, we could imagine rotating the system around so the x-axis becomes horizontal over here, and if so, we'll see that the triangle is going to look like this. I drew this triangle and more or less immediately saw that it wasn't consistent with the idea that this function is decreasing here. So the delta f, well, here's the delta f. That's from here down to here. And here's our delta x from here over to here. Average slope is delta f over delta x. And all the arguments we used, or all the ideas we used in establishing that the limiting value of delta f over delta x as delta x approaches 0 is an instantaneous derivative are going to apply here as well. So I'm not going to go through all of that again. I'm just going to say that, okay, delta f over delta x equals f of x naught plus delta x, y naught, this value, this value, minus f of x naught, y naught, divided by delta x, in the limit as delta x approaches 0, this expression, which I'll just write in the abbreviated form delta f over delta x, becomes what we call fx at x naught, y naught. And the x derivative, since the y-coordinate is not changing as we move in the x direction, is calculated by simply treating y as a constant. So if our function is, again, f of x, y equal x squared y squared plus the square root of y sine of x, then fx of x, y, which we could also write as a partial derivative of f with respect to x at xy, is going to be calculated by treating y as a constant. The derivative of x squared is 2x. Y squared is just a constant that goes along with us. And then it's plus the square root of y, treating y as a constant. Square root of y will be constant, times the derivative of sine x, and that's going to be cosine of x. So, easy calculation. The instantaneous derivative at this point, at this x0, y0 value, is going to be this limiting value of this, limiting value of the average rate of change between the 2 points. And that can be obtained by plugging in the x and y coordinates to this expression.